Good morning. Thank you for coming. So today we have Sergio Suki Messia, who will defend his master thesis on reduced intrinsic neural timescales in schizophrenia during predictive coding. So I will chair the session. So you are allowed to talk between, let's say, 20, 30 minutes maximum, okay? And then they will have questions. This is an exam, so when he finishes, no clapping is allowed. Okay. So the floor is yours.
Okay. Thank you very much. So my name is Sergio Suki Messia. I'm going to present my master thesis project on reduced intrinsic neural timescales in schizophrenia during predictive coding. I'm going to start by giving an introduction on the bias and brain hypothesis, the main idea behind this predictive coding in neural systems, the other important concept, which is intrinsic neural timescales, and the relation with schizophrenia. Further on, I'm going to describe the objectives of this thesis and the model and computational procedure that we've used to make the analysis and find these timescales. I'm going to have a discussion on the most important results and a short summary of what we've achieved. So to start, the Bayesian brain hypothesis is based on the idea that philosopher Helmholtz in 1866 had about perception as an idea of unconscious inference. Our brain has this model of the environment, of how the environment generates the sensory inputs that we perceive. It creates predictions that to minimize the amount of energy that is needed to compute and to take information from the sensory inputs that we receive. And this neural activity is then compared with the sensory inputs that we receive to update the perceptual model that we have. So with this idea, we have a constant prediction and prediction error of our predictive model, and we keep updating as we receive as the brain receives sensory inputs. That's the main idea of the Bayesian brain hypothesis. And then we have the other concept, which is intrinsic neural timescales, in which in literature they are understood as biomarkers for the temporal integration in neural activity. However, in our system, what we have, there are belief trajectories. As we receive inputs, we have this updating of our beliefs, and through these trajectories, we can define a new definition of this intrinsic neural timescale as a marker for trial influence on succeeding values of this trajectory, or in other words, a memory of the hidden states evolution of the states that we don't see that produce these sensory inputs. But however, the computation is still going to be the same. We have we make the autocorrelation function of this trajectory, and the intrinsic neural timescale is the area under the curve until it reaches the first zero value. As we can see here, this area under the curve. With this, why are we studying psychiatric disorders from this perspective? In particular, schizophrenia, because schizophrenia is a psychiatric disorder affecting almost 1% of the population and is characterized by hallucinations, delusions. So this can be directly related to abnormal prediction errors, a wrongful way of how the person is predicting or is processing this sensory information that they are perceiving. So abnormal prediction errors in our different psychiatric disorders. There have been many experimental analysis in which, for instance, in the side of predictive coding, a failure of sensory attenuations in the inputs that we receive produced disruptions in neuromodulators such as dopamine, characterizing the inability to experience happiness, for example, from schizophrenia. And from the side of intrinsic neural timescales, we have that there are generally shorter and inflexible intrinsic neural timescales, while the agents, the participants, are performing tasks and rest states. This is comparing schizophrenia with a control group, a control healthy group. So the idea is to relate these two concepts together and see if we have two main objectives. But relating this by two main objectives. First, understanding, looking at the property of hierarchy of timescales as we go deeper into the hierarchy, and from node 1 to node 2 to node 3, we would like to see higher timescales, higher intrinsic neural timescales node 1 having less than node 2, having less than node 3. Further on, we would like to see with varying the parameters of the model, of our perceptual model, to simulate these disease-specific learning architectures for the tasks they are performing, for the computational tasks that they are performing. With this, simulating schizophrenia-like patients and a healthy control patients, we would like to see shorter intrinsic neural timescales for schizophrenia-like agents, and hypothesize that a higher uncertainty would. Okay, no problem. Yes. They can hear. Yeah, it's
Probably because
esto está entendido, no sé.
Los que estáis online, podéis escuchar la charla, la presentación. Solamente decir sí o no. Okay. Sorry, go ahead.
So we hypothesize that a higher uncertainty estimation will produce a lower surprisal in our system and higher prediction errors. So to start, how is the computational procedure that we use for this model? First, I want to describe how we created the inputs. The inputs follow a task performed by Iglesias et al. In 2013, a procedure from them, and it's a Q outcome task. We have a Q, a low or a high node, and then the patient has some time to create a prediction, and if the next target is going to be a house or a face. So these low and high nodes are associated with a house or a face with a certain association strength, and with this we have these kinds of data series. We have our model, our system, our inputs are going to be separated into two categories, eta 1 or eta 0, with a certain uncertainty that is described as a variance along with these two categories. And we have the possibility of, if given a low node, to have eta 1, a face, or eta 0, a house. With this, we have two different kinds of association strengths, of probability strength, either a probability of 0.9, where almost every time we receive a low node, we can have a face, or almost 0.1, that almost every time we receive a low node, we have a house. This is the high association strength, and low association strength, which is 0.7 and 0.3. That's probability for these relations between the Q and the target. We can see that this task is symmetric. Either we can have both for low node and house is the same as for high node and face. It would be symmetric in that case, and around the 0.5 axis. That indicates the no association strength probability. So with this, how do we describe an agent? How do we describe an agent to generate these, to process the inputs that we are creating? So in our brain, we have this generative model, of the environment. It can be described by a joint probability distribution. With this joint probability distribution, we could get the inputs given our hidden states. However, we need to get the contrary. We want to know the evolution of the hidden states, what we don't see in the environment. So to do that, the first idea would be to use the Bayes theorem and get this evolution of the hidden states with a likelihood, given a ratio between the likelihood and a marginal evidence, and a prior of what we knew. The prior is what we knew from the knowledge that our agent has of the hidden states. Likelihood is how we know the inputs are generated from these hidden states, and a marginal is how good our model it's able to produce the hidden states. However, this would be simple if we knew the form and we were able to calculate these probability distributions. However, in most cases, these calculations are untractable, meaning we cannot solve them, and we need to require two variational approaches, for instance, that were introduced by Friston in 2005, in which we approximate these true posteriors, with this evolution that we want to have, into an auxiliary family of distributions, such as normals or binomials, that we know how to solve. With this, we try to minimize the Kullback-Leibler distance. We try to make these two probability distributions similar, and after some calculation, we can get an upper bound for this distance, which we call the free energy. And this is what in neural systems is called the free energy principle. And it's similar as in machine learning, that is the negative evidence lower bound. Is the negative evidence lower bound. So with this, with this variational approach, we're able to change from an inference problem into a minimization problem of an upper bound of this free energy principle. And with this, using Newton's methods or gradient descent, we're able to calculate the update equations given every time we're given our new sensory inputs. So in particular, we are looking at the hierarchical Gaussian filter, which can be understood as a belief propagation network. We have acyclic hidden states. Our state nodes can be coupled in two different ways. Either a value coupling, the mean of the parent node is coupled with the mean of the child node, or a volatility coupling, which the mean of the parent is coupled with the variance of the child node. In figure B, we can see that how the information flows in these kinds of networks. We have information coming from the bottom levels of the hierarchy and affecting the posterior. The information comes, updates the posterior, creates new prediction errors, and then the information flows higher in the hierarchy. And then once it reaches the top of the hierarchy, the model keeps creating predictions until it reaches the next sensory input. This implementation was made using a Python library that is called PyHDF, with some functions that we have to create that were not implemented yet, such as the precision, including sensory precision into the model. And we've analyzed two different kinds of networks, either the two-level hierarchical Gaussian filter and the three-level hierarchical Gaussian filter. In the two-level, as the name implies, it has two hidden quantities. One is the continuous quantity, a quantity that evolves with a Gaussian random walk, with a normal distribution, and indicates a tendency towards one of the categories. This tendency towards one of the categories then affects a categorical node, which separates between one category eta 1 or eta 0, depending either the house or a face, and then it creates the inputs. It creates the inputs with a certain sensory uncertainty by you. With this, we have that our tendency nodes have a constant variance in these models, constant variance given by the exponential of omega. However, we can include an adaptability to that variance by including an upper level in this hierarchy, a volatility node, which is the X3, in which it estimates with a Gaussian random walk it's coupled with a volatility coupling. It estimates variability inside the variance of this tendency node. It itself affects the level 1. So what is the advantages of this model is that our updated equations can be constructed to be individual for each level in the hierarchy. Even if we change the probability distributions of one level specific in the hierarchy, our equations remain the same, and the only thing that changes is the equation for a specific node. So we can include more nodes, and the equations will remain the same for the nodes that stay the same. So as long as we have sufficient statistics, by that I mean the means and the precisions for the previous values before we receive the sensory inputs, we can calculate the new sensory inputs. So imagine we have a prior, what we know about the hidden states, and we receive a sensory input y. So this would generate a likelihood, and with this we can compute the posterior, that it would be the update, the evolution of our hidden state. So considering that we have a hidden state that evolves as a Gaussian random walk around the mean value around the mean value given from the previous step, we have two steps: the prediction, in which our previous value is going to be the belief value is going to be the previous one, the previous mean, and the precision is going to be an inverse sum of the variances. With this, then the update, how our expected mean of our probability distribution is going to be a sum of what we believed it was going to be, plus a variable learning rate and a prediction error, which is the difference between what we expected and the input that we received, and the input that we believed, what we received and what we believed. With this, we can describe two important quantities, or many quantities, but two of the important ones are the precision-weighted prediction error, which can be understood as a message passing across the different nodes couplings. And it's equal to the ratio between precisions. This is usually a quantity that is found experimentally because it's proportional to what the learning rate, to the update of the learning rate. And this is found in many experimental procedures that use this hierarchical Gaussian filter. Further on, there's the surprise, that is how unexpected our new information is. Given some bottom information at a data point k, we compare that how good is it, how well is it from the perspective of the nodes model, the node probability that it has. With this, I wanted to discuss the analysis. To start, the belief trajectories, we can see that for the categorical node, as the agent keeps receiving inputs, we have this hidden state, this hidden variable, as we've described in the procedure in the computational procedure. We have this hidden variable that is the association strength that generates these inputs. So our categorical node the expected belief of our categorical node is going to try to follow this association strength. As it receives inputs, it updates with some fluctuations due to the sensory uncertainty in the inputs. It's going to follow this association strength. And we can see that these updates are not always consistent. For instance, if we have here all 0.9 or category 1, if we have one category 0, there's a spike in the background. We have the surprisal, and there's a spike in surprisal because it's an unexpected input, and there's a decay, higher decay into the belief trajectory. So, but however, looking at these trajectories, it's really hard to get information to what is actually happening in the system. So, as to what we want to know, that are the intrinsic neural timescales. Therefore, we compute the autocorrelation function and the intrinsic neural timescales, and we can see for our two-level hierarchical Gaussian filter, there's this increase in, you can see here in black the means, and there's an increase in the timescale as we go from node 1 to node 2, and the same happens with the three-level hierarchical Gaussian filter. As node 1 and node 2 are similar, however, there's this increase from node 1 is less than node 2, then node 3 is much higher. So we have this hierarchical property of timescales across both the two-level and the three-level model that we analyze. And I want to remark the fact that both of these nodes 1 and node 2, are really similar. And looking at the autocorrelation function, we can see that node 3 takes a long time to decay, and node 1 and node 2 have similar decaying functions for their autocorrelation. And we hypothesize that this is due to a high dependence on the information that they are processing. Since node 3 is processing information for a volatility, for an error, this means that it's going to take much more memory in order to process this information, and therefore the autocorrelation function is going to decay much lower. However, nodes 1 and node 1 and node 2 are dependent and try to process a category, a tendency towards one category, which can be considered similar information. Therefore, these nodes have similar intrinsic neural timescales. However, still having this hierarchical property of timescales. Further on, we've looked at two different experiments, one for a 2-level hierarchical Gaussian filter, another for a 3-level hierarchical Gaussian filter, comparing both schizophrenia and control patients. For the 2-level hierarchical Gaussian filter, Adams et al. In 2018 showed that schizophrenia patients have a diagnosis, make much larger adjustments with unexpected beliefs and lower and smaller adjustments with consistent evidence. This can be explained by a higher coupling between both nodes, node 1 and node 2 in our Bayesian network, in our hierarchical network, and a higher estimation of the constant volatility in the system. With this, we can see that as we increase the coupling, our intrinsic neural timescale is going to be smaller. Therefore, our control patients, we have less coupling, less value coupling, are going to have smaller intrinsic neural timescales than the schizophrenia patients. This is both for node 1 and for node 2. This increase in the value coupling of the system can be related also with symptoms, the schizophrenia symptoms such as derailment and loosening of associations. And further on, we can see that looking at the measurements, the surprising ones are the surprisal for node 2 and the precision-weighted prediction error. We can see that for our schizophrenia patients, our surprisal and by consequence our precision-weighted prediction error are much smaller, which would be surprising due to the fact that this would mean that our schizophrenic model is generating better estimations of our task. However, this can be seen as from the perspective of the task structure, as we have this symmetry along the 0.5 axis. We can change. We have this symmetry in the task. We have a higher chance of consistent evidence, and so smaller adjustments to possible to consistent evidence. And when we receive unexpected evidence, meaning that the association strength changes a lot, our schizophrenic patient is going to adjust much better to this new association strength. Further on, looking at the 3-level hierarchical Gaussian filter, Desserno et al. Showed that schizophrenia patients have an enhanced choice switching due to a higher initial belief of the error, of the estimation of the error in the environment, the volatility, and a higher coupling strength. We can see this common factor between both of the 2-level and the 3-level, where we have a higher coupling strength. However, right now we're going to have a new factor, that is the initial value of this error estimation. And this factor is going to be really important because with this, the volatility coupling, as we increase the volatility coupling, the intrinsic neural timescale is going to tend to increase. However, due to this higher initial estimation of the error that the schizophrenia patients have, we get a lower intrinsic neural timescales for both in both the categorical and the tendency node, and nothing conclusive for the 3rd layer, since it takes much more time, and maybe with more steps or more agents, it would show a difference, but nothing conclusive from the experiments that we performed. Looking at this volatility coupling, we can see that our model has a higher prediction error, meaning that the schizophrenic patients have worse estimation of what the prediction, the actual value of the volatility is. However, due to this higher initial belief, the message passing, which is the precision-weighted prediction error, which is the message that is passing, that is going along between nodes 2 and node 1 to estimate this error in the environment, is going to be the same, meaning that they both perceive that they're having the same estimation of the errors. With this, to summarize, we've seen that our models, both in the 2-level and the 3-level hierarchical Gaussian filter, they show this hierarchy of timescales. As we go deeper into the hierarchy, higher into the hierarchy, we have a higher intrinsic neural timescale in our system from node 1 and node 2, and it depends on the processed information that is given by each node. Further on, we set the ground for our new definition of how intrinsic neural timescales can be seen from the perspective of belief trajectories, and as a marker for an influence on succeeding evaluations in every time we receive sensory inputs. And we see that specific parameter changes, like an increase in the coupling between the nodes, can reflect disease-specific learning architectures for a task, such as the increasing coupling that we've seen for schizophrenia in these cases, or the increase in volatility estimations. And with this, we can replicate things that have been seen experimentally, such as the lower intrinsic neural timescales for schizophrenia patients compared to control, right? Compared to the blue one. With this, there's this heightened volatility estimations. We showcase characteristic schizophrenia symptoms, such as inflexible decision-making, and many more symptoms from the psychiatric disorders. However, this is just the tip of the iceberg. This is just the tip of the iceberg when it comes to these kinds of research in Bayesian models and psychiatric disorders. And from my perspective, it would be really interesting to see real Q outcome experiments with intrinsic neural timescale from neural activity and intrinsic neural timescales from belief trajectories, which would emphasize and make stronger relationship of both of these definitions of timescales, and analyzing these psychiatric disorders from the perspective of other models, such as new predictive coding, having dynamic belief propagation networks, meaning that we can change the parameters in the model, since in this case we assume that they were static, or having active inference, which has been a really big framework recently, where our actions also affect how we perceive the new sensory inputs. With this, this is some of the bibliography that I've used throughout the work and throughout the presentation. And thank you very much for listening. If you have any questions, feel free to ask.
Thank you, Sergio, for keeping the right time. Can you please stop the recording?